whenever we're dealing with forces, whenever we're trying to understand a situation that involves forces and accelerations, the first thing you have to be able to do is recognize, identify all the forces that are at work in that particular situation. So it would be good if you have a list of the forces that you need to be on the lookout for, a list of the forces that you might expect to see in different situations. And I've written up that list. It's in the Chapter 4 folder in Blackboard. And as you watch this video, it's good to follow along with that list handy. Take a few notes on, write a few notes on that list as I talk here for the next few minutes. So if you don't have the list handy, just stop the video for a minute and make yourself a copy of that list. Anyway, the first force in the list is one we've talked about a little bit already, gravitational force. And we're focusing most of the time on one particular kind of gravitational force, the gravitational force that comes from the Earth and acts on anything that's at or near the surface of the Earth. And the name we give to that kind of force is weight. Weight is just another name for the gravitational force from the Earth, acting on anything here at the surface of the Earth or close to the surface of the Earth. We'll think a lot about weight in a lot more detail later on, but one thing to emphasize right from the start, weight is not the same thing as mass. In everyday speech, weight, mass, weightiness, massive, heaviness are all used more or less synonymously and interchangeably. But to be precise, in physics, weight and mass are two very, very different things. They are not the same thing, and I can guarantee it, you will get yourself into trouble. You will make mistakes if you don't remember that and keep that in mind. There is a relationship between weight and mass. It's right here. The magnitude of weight, the strength of the weight force, is just equal to the mass times g. G is our normal shorthand for the acceleration due to gravity, 9.8. So weight is a force, a particular kind of gravitational force. Mass is not a force, and we'll see what mass actually is later. So second type of force, so-called spring force. This is one force in a larger category that we might call elastic forces. So an elastic object is anything like a spring, anything that when you stretch it or squeeze it or distort it in any way, it will try to return to its original shape. You stretch the spring, it'll try to snap back to its original shorter length. You squeeze the spring, it'll try to snap back to its original longer length. Elastic simply means that the object can, after it's been distorted in some way, it can return to its original shape. So what happens in the case of a spring when it's acting as an elastic object? So imagine you've got a spring here tied down at one end, and I can grab hold of the other end here and push it or pull it. But let's say when the spring is at its normal relaxed length, not squeezed, not stretched, the right end of the spring comes this far. Then I grab the right end of the spring and pull. That means now the right end of the spring has gone through a rightward displacement this big. And since the spring is stretched, it'll try to snap back to its original shorter length. But it can't snap back because I'm holding it. But it's trying to snap back. This end of the spring is trying to move back to where it was, and because it's trying to snap back to where it was, it's pulling on me. It's pulling to the left on me. I pull the spring to the right, and then the spring pulls back on me in the opposite direction. That force from the spring, which comes because the spring has been stretched, the force from the spring on my hand is what we call the spring force. Or similarly, if I push on the spring so that the right end of the spring now goes through a leftward displacement from here to here. If I push on the spring is squeezed, so it's going to try to snap back to its original longer length, but it can't snap back because I'm pushing on it. But it's trying to snap back. It's trying to snap back to its original longer length. So as a result of trying, it's pushing on me. I push on the spring one way, and the spring pushes back on me the other way. And the spring pushes back on me because it's an elastic object trying to return to its original shape. It's always the case in these spring forces and elastic forces in general that whenever there's some kind of a distortion, the spring force is always trying to undo that distortion. In this case, the spring is stretched, the distortion is a stretch, and so the spring force points the opposite way, opposite from the direction of the stretch. And similarly here, where the spring is squeezed, the spring force points opposite to the squeeze, trying to undo the squeeze and return the spring to its original shape. Then there's also a normal force. Normal force is actually another kind of elastic force. Basically what a normal force is a push from a surface. Just think of me standing here on the floor. We know there's a weight force from the earth pulling down on me. We know that gravitational force is pulling down on me, but I'm not falling. I'm not moving at all. So it must be that there's some other force in the opposite direction from the weight, and this other force cancels out the weight so that weight isn't able to pull me down and accelerate me downward. That other force that counteracts the weight is a normal force from the floor, a push from the surface of the floor. And think for a bit about how a normal force happens. It happens because it's an elastic force. So for example, I'm pushing on the blackboard here, but I know also the blackboard is pushing this way on me. If the blackboard wasn't pushing this way on me, I would fall over. Where does that push in this direction, push from the blackboard pushing on me in this direction, or pushing on my hand more specifically, where does that push come from? Well, it comes from the elasticity of the blackboard. Almost all solid objects are elastic to at least a tiny little extent. When I push on the blackboard, the molecules right at the surface of the blackboard are squeezed tighter together a little bit more than they are normally, and they're going to try to snap back to their normal, larger spacing. And as they try to, so I push on the blackboard, squeeze those molecules closer together than they really want to be, they're going to try to snap back to their longer separation, and in trying to snap back, they'll push on me. I push this way on the blackboard so the blackboard is squeezed a little bit. The blackboard tries to snap back to its unsqueezed state. In other words, I squeeze it this way, the blackboard is trying to move this way. It can't move this way because my hand is blocking it, but it's trying to move this way to snap back to its original perfectly vertical shape. And in trying to snap back this way, it pushes on me. That's the source of a normal force. And one thing you notice in both the examples of normal force, they are pushes from surfaces, and the push is always perpendicular to the surface. The normal force from the floor on me, the push from the floor is vertical, but the surface, the floor that was doing that pushing, is horizontal. And in this case, the normal force from the blackboard on me, the blackboard is vertical, but the blackboard's push on me is horizontal. The push, the normal force from the blackboard on me is horizontal because the blackboard is vertical. Normal force is a perpendicular push from a surface. And next force, the fourth force, the fourth force, one more kind of elastic force. A tension force, and I'll usually use just plain T as the algebraic symbol for a tension force. Tension force is, whereas a normal force was a push, a tension force is a pull. A pull from a rope or a chain or a rubber band or a muscle in many cases. And when that rope or muscle is pulled, again, that rope or that muscle is an elastic object. When you pull the rope, the molecules in the rope are now pulled a little farther apart than they really want to be, so they're going to try to snap back to their original shorter length. You pull on the rope this way, and the molecules in the rope are now spaced too far apart. They're going to want to snap back to their original shorter spacing. That is, the rope is going to want to be a little bit shorter, so it's going to try to snap back this way, and as it tries to snap back this way, it pulls on your hand. That pull from an object that's being distorted a tiny little bit, pull from an object that's being stretched a tiny little bit, we call tension. The next three forces are all different kinds of friction force. The first case of friction, imagine two surfaces sliding across each other. A little kid on a sled sliding down a snowy hill, or a skater and the blades of the ice skate are sliding across the ice, or a really icy road, and your tires are just sliding across the road instead of rotating normally. That kind of friction, two surfaces sliding with respect to each other, we call kinetic friction. Sometimes sliding friction, but also more often kinetic friction. Whenever I'm referring to friction, the algebraic symbol I will use will always be a lowercase f, and then a subscript to indicate which type of friction. K indicates that this is kinetic friction. And the thing about kinetic friction is that it slows you down. Imagine that just try sliding a book across the table. You slide it across the table this way. Eventually it slows down to a stop. Well, the book was sliding this way, so velocity was in this direction, but it's slowing down. Remember, whenever something is slowing down, velocity and acceleration point in opposite ways. Velocity points this way, but it's slowing down, so acceleration must have pointed this way. The force that produced that acceleration would be pointing this way, and the force that produced that acceleration to make the book slow down, that's kinetic friction, because the bottom surface of the book is sliding across the surface of the table. And notice one thing about that sliding, the book was sliding this way, the direction of its motion was this way, the velocity was this way, and the kinetic friction force was opposite. That's always the way it works. Kinetic friction will always point opposite to the velocity, always point opposite to the direction of motion. Always pointing opposite to the direction of motion. The next kind of friction deals with an object that's not sliding, an object that could slide, but actually isn't sliding, it's just stuck. And that we call static friction. Static meaning not moving, as opposed to kinetic meaning moving. Static friction will be acting on an object that isn't moving. Kinetic friction will be acting only on an object that is moving, sliding across a surface. Imagine you've got a heavy crate, you're trying to push it forward, but it's not moving. Well, if your push were the only force, then the crate would move forward. But your push isn't making the crate move forward because there's some other push in the other direction that's canceling out your push and undoing any effects from your push. So you're pushing this way, but that force is undone, canceled out by a force in the opposite direction, which is preventing the crate from sliding forward. The force that prevents the crate from sliding is static friction. Static friction prevents sliding. Static friction keeps something stuck in place, static, and keeps it from sliding. For example, go back to that crate. Here's the crate, and here I am pushing on the crate. So we can identify all the forces that are acting on the crate. I'm pushing on the crate, but the crate is not moving. It has a velocity of 0. But what are the forces on that crate? Well, the crate has mass, so it feels a gravitational force from the Earth. It feels weight pulling down on it. But the crate is not falling, so there must be some upward force that cancels out the weight and keeps it from falling. That would, again, be a normal force from the floor on the crate. The floor is horizontal, and the normal force is a perpendicular push from the horizontal floor. And then there's another normal force from my hands pushing on the crate. My hands are a vertical surface, and they're creating a horizontal push, right? A perpendicular push that comes from a surface, that's a normal force. So my push is a normal force. Normal force from my hands on the crate. I write this subscript to distinguish this normal force from this other normal force, which is a force from the floor pushing on the crate. Well, the crate is not moving because this force here, which would make it start moving, would make it accelerate in the forward direction, isn't able to do that because there must be some other force canceling it out. That other force is static friction. Lowercase f because it's a friction force, and subscript s because it's a static friction force. That whenever there could be sliding, but the sliding is prevented, it's prevented because of a static friction force. And note that the static friction force, just like in this example, in every example, the static friction force will point opposite to the sliding that it is preventing. If the crate did slide, if the crate did slide, it would slide this way, but sliding that way is prevented, which means the static friction force is pointing opposite. Static friction force and kinetic friction force both happen because there's little adhesive forces between the molecules on one surface and the molecules on the other surface. So in order to get motion started, you have to break some of those adhesive forces. Or in the case of kinetic friction, you have to continually keep on breaking those adhesive forces in order to make one thing slide across another surface. But because of those adhesive forces, the bottom of the crate might be stuck to the floor, or because of those adhesive forces, the one sliding object might slide only with difficulty over another sliding object. So, those are two friction forces, and there's one more friction force here. One more friction force, rolling friction. And my algebraic symbol there is F subscript R, lowercase f for friction, subscript R for rolling friction. Imagine a ball rolling across the table. It's rolling, but you could imagine, theoretically, you could imagine it sliding across the floor instead of rolling. Just as you could imagine, say, the tires in your car normally will roll as the car moves, but if it's an extremely icy road, the tires could slide instead of roll. So here's a tire, and if the car moves forward, velocity of the car is that way. The wheels of the car will rotate like that, clockwise. That's when there's rolling. If it's a very icy road, there is no rolling, there's sliding instead. So the car is still moving forward, but this surface here is just sliding. There's no rolling. There's sliding in that direction. Rolling friction is what you get when there's at least a little bit of stickiness, a little bit of adhesive force between the molecules in the road and the molecules in the tire. They stick long enough to keep the tire from sliding and make the tire roll instead of slide. Just like static friction, rolling friction prevents sliding. And when rolling friction prevents sliding, just like the name says, you get rolling instead. Just as in the case of static friction, when static friction prevents some kind of a slide, it's because the static friction force points opposite to the slide. Same thing here. If rolling friction is preventing sliding this way, it's because that force opposes the sliding, points the other way. So if you do have rolling friction, a rolling friction force that's coming from the road and acting on the tire, is as the tire moves this way, rolling instead of sliding this way, it's because there's a rolling friction force pushing this way. What actually happens is that there's a little bit of adhesive bond, tiny brief adhesive bond between the road and the piece of the tire that's actually in contact with the road, and long enough for this backward force to actually push this way on that piece of the tire that's in contact with the road. And pushing this piece of the tire this way, of course, is going to make the tire rotate clockwise. So those are 7 forces. One more force, one that we've already alluded to from time to time, so-called drag force. Uppercase D, subscript uppercase F, subscript D is my usual symbol for drag force. Anytime anything moves through any gas or any liquid, say an airplane moving through the air, or a ball thrown and moving through the air, or a swimmer swimming through the water, there's a drag force, because whenever the ball moves through the air or the swimmer moves through the water, the ball is always colliding with lots of air molecules as it moves, and the swimmer is colliding with lots of water molecules. So as ball or swimmer move this way, they collide with lots of air or water molecules respectively, and each little collision is a tiny backwards push. And it could be that under some circumstances, the sum of those tiny little backward pushes might become a significant backward push. The sum of all those backward pushes is the drag force. Sometimes the drag force might be insignificant, sometimes it might be a very strong drag force. One important property of a drag force is that it depends on the speed. The faster you go, the stronger the drag force you will feel. That if the ball is moving through the air faster, it feels a stronger drag force. As the airplane accelerates, as the airplane speeds up, it feels a stronger and stronger drag force. But again, just like in the case of kinetic friction, whatever the direction of motion is, the drag force points backwards, because the drag force is the sum total of all kinds of microscopic backwards pushes. So whatever the velocity is, drag force always points opposite to the velocity, always opposite to the direction of motion, same as kinetic friction does. But the one thing that's unique about drag force is that the strength of the drag force depends on the speed of the object that is feeling that drag force. Higher speed always means stronger drag force. So those are those are the basic ideas. The first thing we'll do in class is practice looking at different situations and trying to recognize what forces are present in all kinds of different situations.